All right, welcome to the session on logic and decidability. My name is Zach and Kate at Princeton University, and we're going to start off with a talk by Xiao on some computability theory as it relates to programming languages.
Hello. Hi, everyone. Welcome to this talk. I'm Shuo from Georgia Tech. And this work is a joint work with Professor Qirun Zhang. This is basically a computability theory result, but it is also related to programming languages in many aspects. First, I want to mention something about the background and motivation. Undecidable problems. This is a class of problems that cannot be solved by any algorithm, and it has been known since 1930s. Examples include the halting problem, the non-trivial properties of programs, and the validity and satisfiability of logic formulas, first-order logic in this case. Okay, we have undecidable problems. They are not solvable in a precise sense, but we can always use approximations. This is also the practical solution that we have. In this case, for example, the polygon represents the undecidable problem, and the small circle inside it represents an decidable approximation of this problem. In this case, it is an under-approximation. We might also consider over-approximations in this case, or maybe something in between. So the general goal of many pure and formal methods algorithms is to make better and better approximations to some undecidable problem. So if we have under approximations, we want to make it larger and larger to cover more and more instances of the undecidable decision problem. So it's like this process. So how to get better approximations? First, we might do some case-by-case work. We can look at the approximation individually. In this case, we can look at how to improve this specific algorithm for program analysis. This is clearly domain-specific. If you are looking at theorem proving, you might look at some different frameworks. And more importantly, there's no guarantee of success. You may or may not be able to figure out where the imprecision occurs in this program analysis algorithm. The other idea is to use the famous framework of counterexample guided abstraction refinement. This is typically used to refine the abstraction for individual programs. Like if you want to verify a property of a specific program, you might want to refine the abstraction for that program. But can we apply this idea to the verify itself? Suppose you verify a field on a program. Is it a counterexample? In this sense, a counterexample means the program is correct, but it is unverified by your verifier. So your verifier is not that precise in this case. But it turns out that even for deciding whether this is a counterexample is undecidable, because knowing whether the program is correct is just the undecidable verification problem itself. So we are going back to the original problem. The issue is we cannot discern counterexamples. Okay, now let me present our main result. The problem is non-computable, which is bad, but we show that for many problems improving decidable approximations, this process could be computable. So this brings a new perspective on the approximation and the undecidable problem, how to view it. Previously, we have like domain-specific ways, like looking at individual algorithms. to say how to improve them. But now we have a completely general method, because as long as the improvement process is computable, it can be specified as an algorithm. No guarantee of success previously, but as long as we have a computable method, it's guaranteed to succeed, because the computable method means the computation must terminate. If we directly apply counterexample-guided abstraction refinement, we have the cannot discern counterexamples problem. But now, we are not actually trying to discern whether a given program is a counterexample to this verifier. Instead, from the verifier, we can compute a program that is a counterexample. I want to make a remark here. This is a theoretical result, and it is not supposed to be directly used. And later, I will give more comments on this remark. Here is our key concept for this result. It turns out that this is a property of the problem, not your verifier, not your analyzer, but the problem itself. An undecidable problem is witnessable if and only if we can find a function such that, first of all, it should be computable. Second, it can transform any approximation to a witness showing the imprecision of this approximation. In this case, we use the symmetric difference P and Q. So this represents the error region of this approximation. No matter it is an under approximation or over approximation or any other case, this always represents the error region. And here, this notation means the code implementing the characteristic function of this approximation. Because we are talking about decision problems, both the problem and the approximation are sets. So we have a set, and we can implement the function, the characteristic function of this set, because it is a decidable set. And this represents the code of that implementation. And this is called the witness of this approximation. With this in mind, let's consider some scenarios like this. We have an under approximation of the undecidable problem. We can apply, as long as the undecidable problem P is witnessable, there is a witness function. So we apply the function to this under approximation, we get something inside the error region. So like this small dot. And we have this counterexample showing the imprecision. We might want to refine or improve the under approximation in different ways. We can probably improve it naively or in some more advanced techniques. But it is always possible to include it to make this approximation better. But for the new approximation, notice that the witness function doesn't depend on the approximation. It only depends on the problem. So we can apply the same witness function to get a new witness. And basically, this process is infinite. You can never achieve the coverage of 100% because of undecidability, but you can always proceed in this direction. So witnessability seems like a very good property. We want to ask which problems are witnessable. Here are three main results proved in our paper. First of all, the canonical example of the undecidable problem, which is a halting problem, is witnessable. And theorem 2 and 3 say that witnessability is basically closed and complements and many-one reductions. This lets almost everything in practice be witnessable, including non-trivial semantic properties of program semantics and validity and satisfiability of logic. The key here is that in practice, how do you even know one problem is undecidable in the first place? You probably want to reduce the halting problem to a problem. But as long as you have a manual reduction, the theorems guaranteed that there is a corresponding witness function to improve approximations. Okay, here is a proof sketch for theorem 1 for the witnessability of the halting problem. Let's revisit the standard proof of the undecidability of halt. Suppose we have a hypothetical decider for the halting problem called halt here. Then using that decider, we construct a larger program so that when you apply the f to itself, in two cases, both of them are contradictions. So we conclude that the halt cannot exist. But how about replacing the halt with some approximation of the halting problem? Here, instead of the halting problem, which is hypothetical, here we have the approximation in our hand. It could be your termination analyzer, or it could be some other approximation that you designed. In this case, the entire program becomes a witness of the approximation. You can verify by considering what will happen when you apply f to itself. If f terminates on itself and the approximation also concludes this correctly, this will be a contradiction. The other case is similar. So the conclusion is that this program is in the error region, which is incorrectly decided by the approximation. And the entire construction could be formulated as an algorithm because it is just copying the code into this construction. So that algorithm is the witness function for the halting problem. Also, there could be many different witness functions, and we just constructed one of them here. Proofs of witnessability is closure and complements and manual reductions. This is basically propagating witnesses along those operations. We refer to our paper for details. Okay, how general is this result? There is only one requirement. You want to implement the decidable approximation in an admissible programming language. What do we mean by admissible? That means the language should have a computable compiler from and to Turing machines. This is basically every language that you can encounter in practice, no matter whether it is imperative, functional, or object-oriented. Those really doesn't matter as long as it is Turing complete and it has computable translations. But there do exist some non-admissible so-called languages. Those are not likely to occur in practice, but they can be constructed in theory, like this Freiburg numbering. So the conclusion is that this result is very general so that it applies to almost every practical programming language. And moreover, inside of the implementation of Q, you can feel free to use any framework of program analysis. You can use different heuristics, and the final implementation doesn't need to be sound or complete, as long as you have a total implementation of some kind of approximation. This will be the only requirement. What are the implications of this work? First, program verification. A very direct way to interpret this result is that for each witnessable verification problem, for example, the problem of deciding whether a program has maybe non-pointer exceptions or not, we are focusing on a problem. And for this problem, there could be many verifiers. But there is a single program that can take any verifier's code as input and produces a program that is correct but is not verifiable by the verifier. Similarly, because this thing applies to any manual reductions from the halting problem, we also have the implication on automated theorem provers. As long as your logic fragment is witnessable, we have a single program translating any prover to a sentence, basically a theorem that cannot be proved by this prover. Here I want to return to the previous remark, why we think this is only a theoretical result. Because in reality, the prover's code could be very large. So if we apply this construction directly, we could get a sentence unprovable by the prover. But the sentence will be typically very large. It depends on how large the prover is. So, but theoretically, that is indeed a theorem that is correct, but is unprovable in this sense. Here, unprovable means cannot be proved by the automated theorem prover. We also have some other results about witnessability. We have seen many witnessable problems, so are there any non-witnessable and undecidable problems? The answer is yes. We can construct such problems by the famous, well-known technique, diagonalization. But those problems are still artificially constructed. They are not trying to model any real case, and we don't claim they are related to practice. But in theory, they do exist. And how many problems are witnessable? A well-known fact is that in decidability and undecidability, the set of decidable problems, the cardinality is if no, it is countable, and the set of undecidable problems is uncountable. Here it is a continuum 2 to the aleph no. But we can further split the undecidable problems to witnessable ones and non-witnessable ones. And it turns out that those two sets have the same cardinality. They are all having the cardinality of the real numbers. Reflection. Actually, the idea of producing witnesses from approximations is very well known in logic in many aspects. We just need to view some traditional results in different angles. Here I want to name two very celebrated results. One is Cantor's diagonal argument, which is suppose you have a list of all real numbers, suppose that is countable, and you construct a real number that is not in this list. But if you view that in a different angle, you might regard that list as an approximation of the set of real numbers. That approximation is really bad, but it is an approximation. So this construction is really like producing a real number on which the approximation is imprecise. And similarly, in Gödel's incompleteness theorem, here we are referring to the first incompleteness theorem. The typical proof is to construct a sentence that is neither provable nor disprovable from a given formal system. This clearly depends on the formal system. But if you view the formal system, the effective axiomatization, as an approximation to the standard model of arithmetic, you will find that this is also computing a witness from approximation. The witness is Gödel's sentence. The sentence and its negation are not provable at all. But you can include either the Gödel sentence or its negation to your axiom set to produce a more precise approximation. Of course, depending on your preference, you may choose either the Gödel sentence or its negation. But the general idea is that here is also like improving the approximations to some direction to model the standard model of arithmetic in a more and more precise way. This concludes our talk, and I'm happy to take any questions, to take key takeaways of this work. Thank you.
Thank you very much. Any questions from the audience?
Thank you. Cool talk. I'm Josh from Cornell, and I was just wondering, so for the procedure that you showed at the beginning with that like iterative closening of approximations to be feasible, you need to have not just a single technique for constructing an approximation in MAND, but a whole like family.
You mean
Side of problem.
so? Are you referring to the process of improving the approximations?
Yeah, like at the beginning, you showed how like the non-circle.
Yeah. So that process could be parameterized by many different parameters indeed. And this brings us many different ways to do this computation. But in any case, we can use a single approximation to do the step of a single witness function to do the step of finding the imprecision of the current approximation, no matter how you got it in the first place. And yeah, and also the witness function could also be flexible in many different ways. You can use different reductions, different diagonalizations to construct such witness functions. Does that answer your question?
More questions?